Okay, welcome to this demonstration of a process that is fundamental to geography, physical geography, and that is sediment transport. Today I'm going to demonstrate that in two ways. First of all, it will be demonstrated in air, so that it's simply gravity acting on the particles being transported themselves, gravity alone, which pulls, as it were, the particles downslope through air. The air is not really contributing to the movement. In fact, in some respect, it's resisting a little bit. And in the second demonstration, we will use water, so it'll be water transport, in which case the water is pushing, as it were, helping to push the particles down. Gravity also is obviously working there, but a lot of the impetus is coming from the water, and the water pushes the particles. This then will lead to a difference in the outcome. What is that difference? Well, I have some particles here, multicolored particles. They are made from this clay. We have red, green and blue, the primary colours, and it's an equal mass of each, and from these I have made these small particles, whereby the red particles, each individual particle is the largest size, then we have the green particles, which are an intermediate size, and then the smallest particles are the blue ones. Now there's an equal mass because each of these colours represents one package, but we have many more blue particles because they are smaller than we do green particles, and there are more green particles than red particles because the red particles are the largest. Now if we compare these, and then we can discuss a little bit of simple geometry. So if we look at these, we have a large red particle, a medium-sized green particle and a small blue particle. The surface area of the red particle relative to its volume or its mass, because we're assuming it's the same density here, it's the same material, the surface area of this is the relationship between the surface area and the volume is such that there's much less surface area per volume, per unit of volume or per unit of mass in this than there is compared to, say, the blue, the smallest particle, which means that per unit of mass, when this moves across a surface and encountering friction, there's more friction per unit of mass encountered in the blue particle than in the red particle, which means that the red particle should be able to travel farther. It should maintain its momentum. Once it's set in movement, the momentum is contained within the mass, so to speak. It will encounter less friction per unit of mass and therefore maintain its velocity, or at least maintain movement for longer, for a greater distance than the blue. So I will say that when I throw this whole bucket, or set this whole bucket of particles in movement, we should expect to see the blue particles to slow down first, then the green and then the red. Of course this will not be perfect, but we should see a general trend in that direction. And I will attempt to make this as mixed as possible. There's no particular order in these to begin with. We'll just throw them down this trackway and see what happens. I think that's a pretty good demonstration of what's happening here. We can see that the blue particles here, we've got a large group of blue here, then come the greens, and the reds have travelled all the way down. Many of them have ended up down here. And this is a typical pattern that we should see when we have dry transport of particles. For example, in a talus, when we get on a slope, we have, or rather a rock face, particles are breaking off from that rock face of different sizes. They could be big boulders or just small pebble size, stone size pieces falling down, various sizes falling down, and they will travel farther. They build up speed because of gravity falling off of the rock face through weathering of some sort, and they fall down. The larger particles should travel farther down the slope and end up farther away, where we will see larger boulders in the forefield, as it were, to this talus cone, and then higher up we should see the smaller material, generally speaking, as a general rule of thumb for how the particles should distribute. So this process we should see when we have dry transport. This is a typical distribution of that sort. and take a quick pause, and then I'll set up for the wet demonstration. Okay, let's see if this works. I've not tested this yet. So I've got the coloured balls in here and water here. Yeah. So how best to do this? Let's just tip a little bit of that out. Put those in there, and then well, that's not bad actually. Yeah, I think that works as a pretty good demonstration. Not perfect, but we do see the opposite effects. The balls that have travelled farthest are the blue ones, the particles in our case, and the red ones have stopped. A little bit of a disturbance up there, but never mind that. This distribution looks pretty much as I suggested it would do. So I think we can be happy with that. The water has pushed the particles along. The water had the energy, had the momentum in this system, was pushing the particles along. And because of that, as the water slowed down, it couldn't manage to push the red particles anymore, so they dropped out first. Then the green particles, sort of. And then the blue particles, they could keep travelling on with the water because they require the least amount of movement in the water, energy in the water, in order to be transported. So they carried on with the water as it travelled down the track here. So the red ones drop out first because they require more energy to keep them in movement, and the water, as it slows down, loses energy, so they drop out first. The green ones, slightly smaller, should be able to travel a little bit farther. Distribution isn't perfect here. And the blue ones, as I said, they require less energy to keep them in motion, and so they fall out last.